Okay. Well, I'd like to thank everybody for showing up. I guess it's Saturday morning, although it feels like Friday night. But um, anyway, so as I said, as I kind of said, this is aimed at a colloquium level. Hopefully, I've actually hit that level, but we'll see. So let me get started with some motivation here. So a lot of this comes out of special functions, and special functions is basically about functions that show up a lot and are very useful, and then we generalize them, and then they turn out to show up a lot after we generalized them, and they're very useful, and so we generalize them further, and so on. So there's a big theory of special functions of various different kinds. But one of the really early ones, and one of the basic ones, is Gauss's hypergeometric function, 2f1 ABC, and with variable z. And one of the things it satisfies, I mean, there's a lot of different characterizations of it. You can write it as an integral and so forth. There's a power series expansion. But for present purposes, what I want to talk about is the differential equation it satisfies. And so in particular, there's this very nice differential equation. It has rational function coefficients, and well, basically polynomial coefficients, but you could also divide by z1 minus z. And depending on a couple of parameters, and you basically solve that equation subject to the condition as a holomorphic at 0. Okay, now the significance of this equation, apart from the fact that Gauss realized he had satisfied the hypergeometric function satisfies it, is so it's a Fuchsian differential equation. It has three nice singular points at 0, 1, and infinity. So those are the 3 points where you can't just specify the initial conditions and have a solution. And moreover, so those are the 3 points where it's singular. And if I tell you the way in which it's singular there, so basically how the local solutions behave near those points, then that actually uniquely determines the equation. So in particular, the sort of local information I mean is the fact that at z equals 0, there's a solution which is holomorphic, and there's a solution which is basically looks like z to the 1 minus c times something. And you can see that just purely algebraically from the equation that you have those two sort of behaviors of local solutions. Okay, and then that information uniquely determines the equation and gives you this hypergeometric equation. Okay, now another family of special functions, this is a lot later. I guess it was originally found in the early 1900s, but not really all that useful until the late 1900s, early 21st century, are the Painlevé transcendents. And again, these are related to differential equations, although this is not how they were originally discovered. So now basically you say, let's look at a differential equation, again with simple singularities, Fuchsian singularities. But now you have a fourth singular point. Then, so now you have, again, you can talk about the local structure of the equation. And there's basically 4 parameters for the local structure of the equation. But, right, but specifying the local structure of the equation no longer uniquely determines the equation. And so you basically now need 2 more parameters to tell you what equation you have, given that it has these particular exponents around the 4 singular points. Now, one of the things that's interesting is that the parameterization of the equation, if you set it up right, basically doesn't depend on lambda. So you get basically this one family as lambda varies of equations. Okay, now there's another thing you can look at here, which is, you solve you have this equation that has these 4 singular points. And so if you started at one point in C and analytically continue around a loop, and that loop goes around one of your singular points, you're going to end up with in general, a different solution. But you have still, it's a second order equation. So you have a 2-dimensional basis of solutions. And so if you take that basis of solutions and analytically continue around, you're going to get a new basis of solutions. Or in other words, you're getting an element of GL2 of C. And so in particular, this gives you a representation of the fundamental group of C minus those 3 points. So in other words, basically the group of loops mod neighboring loops are going to do the same thing. Okay, and this is called the monodromy representation. Now, the interesting thing is that, so the monodromy representation, you have these three generating loops, basically. You have a simple loop around 0, simple loop around 1, simple loop around lambda. And those generate the fundamental group, it turns out. And those three matrices determine the representation. It's basically, it's just a free group. So you just need to specify those three matrices. But the product of those three matrices, you can think of as a loop around infinity. And so the product also is sort of a natural matrix inspection. So you really think of it as you have four matrices that multiply to 1. Okay. And given that, well, the singularity information tells you the eigenvalues of those four matrices. They're basically the exponentials of the exponents, because you're basically you're going around a loop, and if your thing locally looks like z to the alpha, then that solution is going to get multiplied by e to the 2 pi I alpha if you go around a loop. So you get the eigenvalues of these four matrices from the singularity information. And another parameter count basically tells you that you have two auxiliary parameters to determine the monodromy given the singularity information, given the eigenvalues. Okay, now the fundamental group is just this free group, and so it's independent of lambda. And so if you change lambda, you can ask whether you get the same monodromy. And well, so of course now you have this two-parameter family of equations and it's two-parameter family of monodromy. So you really have this map from equations to monodromy, which is this analytic map. It turns out it's actually biholomorphic if you modulate a little bit of boundary behavior. And so if you start with an equation, it determines the monodromy, and then you can change lambda slightly and go back to an equation. And so this actually gives you now a flow as you vary lambda in the space of equations. And as I said, the parameterization can be done in basically a way which is independent of lambda. And so you now have these two parameters that satisfy a differential equation corresponding to this flow. That flow is a nonlinear second order differential equation. It's still second order because there's two parameters. And this is what's called the Painlevé 6 equation. Now, I'm not going to try to write this down. I'm going to skip a lot of details here. Hopefully I'll be able to give some details and stuff in November for the stuff that's actually like what I'm doing. But this is assuming I'm actually allowed to go to Japan in November, so who knows. But hopefully. Anyway, but it's what it originally arose as, and you can actually, it turns out the fact that it satisfies this property follows from this differential equation interpretation. But basically, if you solve this equation, it's this nonlinear differential equation, those are going to have all sorts of nasty things happen. And in particular, when you try to solve it, you often will get essential singularities popping up. And it's easy to cook up examples where the essential singularity depends on your initial condition. But the Painlevé equations, when you solve them, the essential singularities don't move. So you'll get poles that can, and they can show up and move around a lot. But the essential singularities don't depend on your initial conditions. And it turns out, and so Painlevé, and then had a few holes that were fixed by a student, Garnier. Was Garnier? I think it was Garnier. But basically classified those equations. And there's a few of them that are pretty classical, like the Weierstrass. If you differentiate the Weierstrass equation, you get a second order nonlinear differential equation that all of its solutions just have poles and then essential singularity of infinity. So it satisfies this. But then there's basically 6 more cases that aren't these classical elliptic or even simpler examples. And that's Painlevé 1 through 6. Now I should add the 21st century enumeration has something like 8 examples. So how you distinguish cases is not entirely canonical. And Painlevé does not distinguish cases in the way that we would do things now. But in any case, all 6 of these sporadic cases have interpretations as monodromy preserving deformations of equations, where now the equations may have worse singularities, and you may have to preserve a little bit more than just monodromy. But basically, it's a similar kind of flavor. Particularly, the key information is that as you vary lambda, it turns out the fact that the monodromy gets preserved means that as you vary lambda, the solutions get carried along of this linear equation. Okay, now both of these things have been generalized to death. So for the hypergeometric function, there are certain nth order linear differential equations that are also still rigid and Fuchsian satisfied, determined by their singularities, and those solutions have either nice power series representations or nice integral representations, and they've several of those have appeared in the literature as interesting hypergeometric functions. And also more generally, of course, if you have you could have more than 4 singular points for a second order equation, in which case you're going to have more parameters, but you can still, it turns out, talk about the monodromy preserving deformations. Now, another thing that can happen is that if you take your singularity information, as I said, you're exponentiating that exponent to get the actual eigenvalue of the monodromy. So if you add 1 to one of the exponents, that doesn't actually change the eigenvalues of the monodromy. And so this gives you now some discrete shifts you can do. And now it turns out there's a global condition, so you have to do you have to shift some things up, some things down. But this gives you these discrete shifts of your singularity data that don't change the family of monodromies. And so again, you can start with an equation, map it to monodromy, shift your parameters now by a discrete shift, and map back. And the resulting equation, well, it's now a difference equation rather than a differential equation, but it's still reasonably nice. It's a nonlinear difference equation with rational function coefficients. So it's still pretty nice. Now, these actually originally arose as transformations of Painlevé equations themselves, the so-called Becklin transformations. But then some of them, but they also have these isomonodromy interpretations. Okay, and similarly for the 2F1, we had these 3 auxiliary parameters A, B, and C that were basically telling us the singularity data. You can shift A, B, and C by integers and get a new hypergeometric function. And it turns out when you do that, so the hypergeometric function turns out to also satisfy a recurrence in A as a result. And the recurrence is rigid in the sense that it's a difference equation. If I tell you where that difference equation is singular, it uniquely determines the difference equation up to changes of basis. Okay, and you can go further along the difference equation line. There are some interpretations of Painlevé equations or discrete Painlevé equations as flows in families of difference equations that satisfy something like the monodromy preserving property. In particular, the solutions of the equations carried along in a natural way along the flow. Okay, so that's sort of a bit of setup and sort of why some of these functions are interesting, and in particular why families of difference equations with specified singularities, of differential or difference equations with specified singularities are interesting. Now, as I said, the Painlevé equations had this original interpretation as this sort of, the essential singularities don't move. It's called singularity confinement. And that interpretation actually led to this great paper by Sakai that constructed sort of all of the known difference versions of Painlevé and a number of new difference versions of Painlevé, and got them all in this one common framework involving the algebraic geometry of certain types of rational surfaces. And in particular, one of the new ones he got, and the one that was at the very top of his hierarchy, is the elliptic Painlevé equation. And so you get this new equation, but the problem, one of the things though, is that in that hierarchy, as you get high enough up in the hierarchy, he was getting it from singularity confinement. He wasn't giving a monodromy preserving interpretation. Okay. Also, there are elliptic versions of hypergeometric functions, and sort of the main class of those satisfies a second order rigid equation, and there's some slightly more complicated ones that satisfy higher order rigid difference equations. And so in general, this suggests that we ought to look at families of elliptic difference equations with specified singularities, and they should be related to either the elliptic Painlevé equation or these rigid equations, or if we have more parameters, to higher versions of Painlevé, so to higher order nonlinear equations generalizing Painlevé. And there's, as I mentioned already, for the differential level, there are things like that, like Garnier equations, that are such generalizations. And another thing that one would like to have is an explanation for why. I mean, there's one explanation from Sakai's perspective, but why should we stop at elliptic curves? Why can't we go farther? Higher genus curves or what have you. So let me now talk about what are we actually classifying here. What do we? So the general game is going to be, we're going to be specifying a type of equation and information about how it behaves near singularities. And then we want to understand the family of such equations. And so, and this is going to end up being an algebraic geometric object called a moduli space. And so we want to understand the moduli spaces of equations with specified singularities. Okay, so first question is, what are the types of equations we're looking at? Well, the standard equations are, you have differential equations, and it's nice to think of these in matrix form. So typically you have this n by n matrix A, and you're looking at looking for solutions of V prime equals AV. But from our perspective, what we want to classify is the matrices A, given some information about how the singularities are, like in this case, basically the poles of A. There's ordinary difference equations, where now A is a multiplicative thing, and you get V of z plus 1 equals A of z V of z is your equation. Now, the singularities here are places where A has a 0 or places where A has a pole. And then there's some slightly weird things that happen at infinity, where what it means to be singular at infinity is slightly non-intuitive. And then how you classify singularities at infinity is actually a significantly complicated thing in general. And then there's Q difference equations, where you replace z plus 1 by z goes to z times q. And again, there are these Q Painlevé equations that in Sakai's hierarchy and Q hypergeometric functions. So those definitely live everywhere. And those are, early 20th century versions of hypergeometric functions, for instance. Okay, now it turns out actually, from some information I had for what the equations related to elliptic Painlevé ought to look like, I had a little bit of extra information. And one of the things that I found was that the elliptic equations weren't just a simple equation where you replace, z goes to z plus 1 or z goes to q times z by a translation on an elliptic curve, which gives you a standard elliptic difference equation. They actually satisfied a symmetry property. And so for an ordinary difference equation, a symmetric ordinary difference equation, it doesn't just satisfy v of z plus 1 equals A of z, v of z. You also have an additional equation, v is minus z equals v of z. Now this forces a consistency condition on A of z, where basically something like A of 1 minus z times A of z equals 1. So you get this consistency condition in order to actually have any solutions. But this gives you a different class, slightly different class of equations. And it's mostly the same, but again, you have this consistency condition, and what you now have these extra points, these half integers here, where what it means to be a singularity gets a little bit more complicated. So for instance, v of z plus 1 equals minus v of z, with that extra condition, actually a singular at v is equals to a half, because there's no holomorphic solution there. So things get a little bit more complicated, but you have this extra symmetry. And in fairness, it does change the moduli space questions, because now the singularities naturally come in pairs, and you should really only count one singularity from each pair towards your complexity of your equation. And similarly, for the Q difference equation, you have z goes to 1 over z, and for an elliptic equation, you have the negation on the elliptic curve, giving you this consistency condition. Okay, so then the question is, given such an equation and type of singularities, how do we classify this? So why do you get into geometry? Well, one issue, apart from the fact that this is an algebraic geometric question to do this classification, well, one of the things is that we've written these as matrices. But if you try to actually do the flows in the differential case, you'll find that as you hit typically poles of your Painlevé function, the matrix form breaks down. And you can often write it as a straight line equation there, but a more natural way of fixing that is to say, well, okay, actually, a differential equation is a connection on a vector bundle. And so, a connection on a trivial vector bundle is just v prime equals a v, but in general, the vector bundle will become non-trivial. So, and then there's something similar you can do in these discrete cases where basically you say, okay, it's a meromorphic map between a vector bundle and its pullback through this translation. And similarly for the symmetric cases. But vector bundles are more complicated. And in particular, this means suddenly that now you have this vector bundle on your curve that you have to put into the data. So you now have a sort of all the complexity of constructing moduli spaces of vector bundles, which there's theory for, but you can't write them down explicitly at all. And then you have this extra data on top. So suddenly you have this thing which is in principle something you can solve by standard algebraic geometric techniques, but it looks like it's going to be a pain. And part of the problem is that these techniques give you moduli spaces, but they do it by basically by changing your equivalence relation, throwing away some points and then weakening your equivalence relation on some other points. And so it's typically not clear how to actually interpret the points where you changed things, what the new equivalence relation is, or what the condition is on what you're throwing out. So this is a bit of a problem. If you want to get a natural moduli space, it's going to be really hard to do. And so the standard technique for solving a hard problem is either make it harder or find a way that somebody already solved it. So, and this is what leads to more algebraic geometry. So if we forgot about the connections on vector bundles and just say, let me classify matrices, well, you still need to fill in something on the boundary. But that something on the boundary you're filling in is now, rather than a connection on a vector bundle, it's just basically a linear transformation of a vector bundle, generally with poles. And this is something which is a lot easier to deal with. And it turns out you can actually turn it into a classical algebraic geometry classification problem. Namely, you no longer, instead you now have a surface, and this commutative relaxation of a connection can be translated into a sheaf on that surface. And sheaves on surfaces, on commutative surfaces, is a problem where somebody's already done all the hard work of making this geometric invariant theory machinery actually give you a sensible answer. Okay, so if we do, so for the wrong problem, it's solved. Module is this translation. So now we just need to figure out what the right problem is, how to tweak it to make it, how we've sort of made the problem harder so that we can still solve it. Okay, so, and this is what leads to non-commutative geometry. So how do you think about differential equations when you're doing algebraic geometry? So you can do it as connections on vector bundles. I mean, those are annoying from an algebraic geometry perspective already. So typically what one does instead is considers what are called D modules. And that's this calligraphic D here is just basically the algebra of differential operators on your curve. So you have your curve, you have these algebra of differential operators, and you're just looking at modules of that. And I'm just glossing over some sheafy bits in this picture, because of course it's a projective curve, so it's really a sheaf of a sheaf of differential operators. Okay, but given this module, mouse from that module into a standard module of basically the module of holomorphic functions or meromorphic functions or functions which are holomorphic away from your singularities, those sorts of those are also naturally modules over the algebra of differential operators, and maps from a given module to that module of all homomorphic functions basically give you the classification of maps from a given module to that is given by the solutions of a differential equation. And so basically you just turn your differential equation into a module that has such that maps of that module are the solutions. Okay. And so for instance, for a straight line equation, you just basically have the quotient of the full algebra of differential operators by the differential operator that that's supposed to kill your function. And then maps from that to holomorphic functions are the solutions of that equation. And then you do something similar for matrices. Okay, so now this algebra, the algebra differential operators, from a high level perspective, like if you do just from the affine line, they're generated by the coordinate and differentiating the coordinate. And those two elements satisfy one relation, which is basically that the commutator of differentiation and your variable is 1. And from that relation, it's easy to figure out what a basis of the algebra of differential operators is. Namely, it's basically monomials in X times monomials in differentiation in X. Now, as I said, I'm glossing over some stuff because this is only a local picture of what the algebra looks like. But there's algebraic geometry that then glues it back together. So what we can think of it is, so basically we can think of this relation here. If you say rescale differentiation by h bar, you can turn the right-hand side into h bar. And then if you take the limit as h bar goes to 0, this relation suddenly becomes, hey, these things commute. And when they commute, okay, you have x, which is just basically the coordinate on your curve, and the limit of dx, which is a new coordinate. And so you get basically just an affine line over your curve. So you basically get this A1 bundle of your curve, and that gives you this an algebraic surface. So, and if you look carefully at what's going on with this this translation I didn't tell you about what the details of, it turns out that basically the translation from relaxed Sheaves, that means relaxed equations to Sheaves, is exactly this relaxation. So it exactly maps into this particular algebraic surface. Sheaves on this. So the point is then, Sheaves on that algebraic surface corresponds to D modules except that we took h bar to be 0. So morally, differential equations or difference equations of the type we want to consider should be modules, i.e. Sheaves, on non-commutative versions of A1 bundles. Okay. Now, one thing if you know algebraic geometry is that it's always easier to do algebraic geometry when things are compact. Boundaries always get in the way, and I mean, holes always get in the way and make things like, gives you infinitely many functions, and life just gets a lot more annoying. So we actually want to compactify things. Now, so what we're going to do is instead of taking a one bundle, which turns out is not actually the right thing anyway when you're dealing with, say, Q difference equations, but instead of taking a one bundle, we're going to take a P1 bundle. Well, and that's going to be what we take the non-commutative version of. Okay. And so we're going to get, so in other words, we're having this what's called a ruled surface. So we have this a surface, a projective surface, a mass to a curve, and the fibers are just lines. Now, there's already some indication that, there was an earlier indication that this sort of thing was the right thing to do, which is that some work of mine with Okunkov, where we gave a construction of elliptic Painlevé using non-commutative geometry, but now basically rather than taking a ruled surface, we took a projective plane. So there's this standard construction of elliptic non-commutative projective planes, and it turns out that modules on that, basically graded modules on that graded algebra could be used to construct elliptic Painlevé.
Excuse me.
Yes.
I have a question. So
Sure.
I understood the differential equation should be a non-commutative bundle over A1 or some non-commutative module over the surface, but why you can also view the difference equation should be such a...
Well, so for the low-level versions, it's not too hard to understand because, for instance, you can replace differentiation by a shift. And so variable and shift. So for instance, for the Q difference equations, variable and multiplying variable by Q, well, they no longer commute or anti-commute, I mean, but they satisfy this Q commutation. So basically, shift times X is equal to Q times X times shift.
But
and again, that when you take Q equals 1 becomes commutative.
Oh, okay.
Now, for the higher level things, it's more of a leap of faith that, hey, maybe this can be made to work.
Okay.
So, because in fact, what the way the actual proofs end up working is you take existing constructions of non-commutative surfaces and show that modules on those actually have interpretations as equations.
Okay, yes, I see. It's backwards interpretation.
So you start with a few cases where you know things, and then you say, okay, well, let's try this because we need to do something. So yeah.
Thank you.
Sure. And yes, and please do ask questions. Okay. So this leads to the natural question of what do I mean by a non-commutative algebraic surface? Now, there's some definitions out there. None of them are really satisfactory. So there's some nice definitions in terms of here's a bunch of axioms, and well, okay, we don't know of any sporadic examples that satisfy those axioms, but all of the things that we know how to construct, I can show actually satisfy more natural axioms. So it's hard, we're not really sure what the right definition is. In particular, the original constructions said, okay, what is a projective surface? Well, a projective commutative surface you can get from a graded algebra. And sheaves on the projective surface are basically graded modules over that graded algebra, modulo killing off some stuff in finite remaining degrees. And that works well for instance, non-commutative projective plane. But it turns out that, so you just deform the graded algebra. But it turns out that for a lot of the surfaces we care about, there's no way of deforming the graded algebra. So the only graded algebra, for those of you who know algebraic geometry, the only things that have a hope of deforming as graded algebras are Del-Pezzo surfaces. And there's just too many interesting rational surfaces too many interesting surfaces that aren't Del-Pezzo surfaces. Okay. The other thing you traditionally do in commutative algebraic geometry is you would say, okay, well, a projective surface is glued together from a bunch of affine surfaces. And an affine non-commutative surface is just a ring, that's fine. But gluing doesn't work. So there's no topological space to start to glue things in. Now, what does work pretty well is a projective surface is actually uniquely determined by its category of sheaves. And we don't mind focusing on the category of sheaves because in the end, we're classifying sheaves. So if we understand the category of sheaves, whether there's an actual surface with that category or whether just some abstractly defined category, doesn't matter because we still have this moduli space of sheaves that we can play with. So what I'm going to take as sort of this vague definition of a non-commutative surface is this is a abelian category. So it's the category of sheaves on the non-commutative surface, really. And it looks like, in some reasonable sense, the category of sheaves on a commutative surface. And what looks like means is basically what gets into these different definitions. So in the end, basically, you construct a category of sheaves and then try to show that it has all sorts of nice properties that are natural extensions of commutative things. Okay, so there are three constructions in the literature of things that are clearly non-commutative surfaces by any reasonable definition. First is non-commutative projective planes. This is generally called the Sklianin algebra. This comes from a graded algebra. It's called the Sklianin algebra. It actually was not due to Sklianin, but it's the usual tradition of never naming things after who actually came up with them. So you have projective planes. There's also a construction of ruled surfaces, non-commutative ruled surfaces, more generally P1 bundles, due to Vandenberg. And Vandenberg also has a construction of blowing up points on surfaces. Now, there's a bit important technical issue there that non-commutative surfaces, what it means to be a point is already a little bit technical, and so you very often only have a relatively small number of points. Like you'll typically only have a one-dimensional family of points. Okay, now all of these constructions are there. None of them involve difference operators or differential operators. However, it turns out that there's an alternate way of getting the same non-commutative ruled surfaces that Vandenberg gets, using something called a Heck algebra, which is basically something I'd come up with at the elliptic level, and then sort of hand waved what it ought to look like at lower levels, and then showed that what you got out of that actually did give you the same category of sheaves as Vandenberg. But these Heck algebras actually involve differentiation or difference or shifts of your variables. So the Heck algebras actually have a natural interpretation in terms of operators. And then turns out that sort of leads you naturally to a way of simplifying the construction, a Merida equivalent construction of your category that actually does directly involve operators of the kind we want to look at. In particular, in the high level cases, what you end up getting are not just difference operators, but symmetric difference operators. And you get this, so you get this natural representation of this category of sort of certain maps in this category as difference operators with the appropriate symmetry. And as a result, this lets you turn all of the difference equations we talked about earlier, all those types of equations can be turned into sheaves on non-commutative ruled surfaces. Okay, and there's a rough converse that every interesting non-commutative ruled surface has an interpretation in terms of difference or differential operators. Where by interesting, I mean it actually arises as a deformation of a commutative surface. Or the other, it turns out, surprisingly equivalent condition is that it's not just a finite dimensional algebra on a commutative surface. Okay, now, so this gives you families of equations. This will turn equations into sheaves. But remember, originally, I didn't just want the equation, I wanted to also understand the singularities and specify the singularities of the equation. It turns out this is actually already present and is a big thing that we get out of having compactified everything. Because since we compactified stuff, we had this notion of what's going on at infinity, the stuff that we added in order to compactify. And that actually turns out to be a commutative curve, even though we were on this non-commutative surface. And so we can take our sheaf and restrict it to this commutative curve to get a sheaf on the commutative curve. And the singularities, in the cases where it's sort of easier to understand singularities, the singularities are exactly given by that sheaf. So if I tell you that sheaf, that tells you what the singularities are. And then more generally, you can sort of classify, given what that sheaf is, what it tells you locally about the structure of the curve. And in general, it always tells you behavior what it tells you about the local structure of the equation. And it's always telling you about local structure of the equation near a singular point. Okay. It turns out it's not always exactly equivalent to the classifications of local data in the literature, but it's always sort of reasonably natural. Okay. So what this says then is that what we're actually looking at is, so the thing we actually want to classify are sheaves on the surface that have a particular restriction to this curve at infinity. And this also in particular explains why elliptic curves are showing up. Because the curve at infinity, this commutative curve, has arithmetic genus 1 for these nice non-commutative ruled surfaces. And so in particular, they look vaguely like elliptic curves. In particular, if it's a rational ruled surface, if it's a ruled surface over P1, it really is, in the most general case, an elliptic curve. Okay. Now, the problem is, so the data about what's the order of the equation and what's the degree of the coefficients, that's something which just directly translates into natural information about the sheaf, the Chern class if it's on commutative surface, first Chern class. However, the restriction to this curve at infinity, what I call the anticanonical curve, because that's what it is in the commutative case, that restriction is not something that's normally dealt with when you classify sheaves. So we're still not quite in the case where somebody's already solved the problem for us. However, what you can do is you can use the fact that we have more constructions we can do. And in particular, we have this blow-up construction. And in the commutative case, if you blow up a point where your sheaf meets the anticanonical curve, it turns out that it actually separates your sheaf a little bit, at least somewhat, from the anticanonical curve. It reduces the extent to which they intersect in general. And so what we can do is we can take our situation and just keep blowing up points until they become disjoint. And so now we have this iterated blow up of a ruled surface, but now we're classifying sheaves that are disjoint from that, from the anticanonical curve. That's an open condition. So that's now just an open subspace, open subscheme of the classical moduli space of sheaves. Of course, this is on the non-commutative surface, so we still have work to do. But on the commutative relaxation, this completely solves the problem and tells us, yes, this is how you construct the moduli space. Okay, so now really what we need to do is we need to understand non-commutative surfaces and show that we can we can do what I call filing off serial numbers of the arguments in the literature. You just basically need to figure out, you look at a book on how to construct the moduli space of sheaves on a commutative surface, and then figure out what you need to tweak or what you need to prove in order to get that same argument to work. And in general, and we can in fact do that, at least for the sheaves we care about. Now, for commutative surfaces, one of the things that's important is that we have these three constructions in commutative land as well. We can P2, we can construct a P1 bundle over curve, and we can blow up points. And these satisfy a bunch of relations. If you blow up a point in P2, it's a ruled surface. P1 cross P1 is a ruled surface in two different ways. Blowing up two distinct points, it doesn't matter what order you do them in, and things like that. And basically none of these were known in the non-commutative case. So that's one of the things that I needed to do, and it's something that I'll definitely be talking about in November if I'm allowed to come to Japan, is how one actually makes those work. And it's definitely much more subtle in the commutative case, which is all just basically local manipulated equations. In the non-commutative case, you actually have to look at the derived categories of these non-commutative surfaces, at least for the argument I have. But given that, one ends up with the following theorem. Well, firstly, that all of the relations are basically still satisfied. So all of the different ways of writing a commutative surface as a blow up of a P2 or ruled surface, all of those relations are satisfied, have analogs in the non-commutative case. And so in particular, if you start with a non-commutative projective plane or a non-commutative ruled surface, and then do a sequence of blowups and blowdowns, and blowdown actually wasn't really constructed in the literature, but you just basically say, okay, well, if you could have gotten it by a blowup, we'll call that a blowdown. Any non-commutative surface you get like that is going to be either a non-commutative projective plane or an iterated blowup of a non-commutative ruled surface. Moreover, any one of these ruled surfaces lives in a natural one-parameter family where one of the fibers is commutative. And if you have a non-commutative family that becomes commutative, that induces a Poisson structure on the commutative thing. And that Poisson structure vanishes on this anticanonical curve, which turns out to actually be fixed in this one parameter family. And the base of this family, the extra parameter in this family that's making you non-commutative, is an element of the Jacobian of the kernel of the Poisson structure. So in particular, when the Poisson structure, when your anticanonical curve is smooth, it's a point on an elliptic curve. When the anticanonical, which is what the thing you're translating by your difference equations, when it's for instance, a nodal curve, it's Q, it's a point in the multiplicative group, and similarly it becomes H bar when it's an additive, when it's say a cuspidal curve or a worse curve, a non-reduced curve or what have you. And so you get this H bar, which is basically the ordinary difference or differential case. Excuse me. Now, so that's for surfaces. Now for sheaves on surfaces, the first thing is that you can construct the moduli spaces. So for at least for one-dimensional sheaves, which turn out to be the ones we care about, there's a natural analog of the standard class construction of semi-stable moduli space. So there's a projective scheme that classifies one-dimensional sheaves and where with an interpretation of what it actually means for two different sheaves to correspond to the same point. It's basically saying that they have a filtration, then there's a natural filtration and the subquotients are just moved around. And this behaves well when you vary the surface. And moreover, and this is something which was mainly known, which was basically known in the commutative case, modulo some issues about the semi-stable part, the compactification, is that the moduli spaces themselves have a Poisson structure. So they themselves sort of have this infinitesimal non-commutative deformation. And in general, and analytically, if you have a Poisson structure, this gives you a foliation by symplectic manifolds. This is not guaranteed in the algebraic case, but in our case, it actually still exists. So there's this foliation by symplectic moduli spaces, and these symplectic spaces you get are just fibers of the restriction of the anticanonical curve. So in particular, so we didn't actually, it turns out we didn't have to have done the blow up. We could have started with just these sheaves on the non-commutative surface and taken the symplectic leaves of the Poisson structure, and those are, at least for the nice symplectic leaves, precisely classifying difference equations or differential equations with specified singularities. And because these behave nicely in the commutative relaxation, you get some nice extra properties like they're rational moduli spaces, things like that. The Poisson structure can be generalized all the way. There's this notion of, you can look at the derived category of this commutative category of sheaves and look at objects in that, and those are classified by something called a derived stack, a derived moduli stack, and that derived moduli stack has a Poisson structure. So there's definitely a lot of generality for this Poisson structure. But so we get this in great generality. Now, one of the things that's interesting here is that I said that, so given a sheaf on a ruled surface, there's an interpretation as an equation. But if I just give you a sheaf on a surface, that's an iterated blow. If I don't tell you how it's an iterated blow up of a ruled surface, there's going to be, it will typically have multiple interpretations as an iterated blow up of a ruled surface. And changing the interpretation changes the equation. And in particular, one of the cases, and remember P1, I mentioned P1 cross P1 is a ruled surface in two different ways. And this, again, carries over to the non-commutative case, which means if you have a sheaf on a non-commutative P1 cross P1, that sheaf, that one, and it came from an equation in one ruling, it turns into an equation on the relative to the other ruling. And that other equation can look very different. So one simple thing that already happens is that the order of the equation changes. Roughly speaking, you swap the order of the equation and the degree of the coefficients. But moreover, it can also change the qualitative type of the equation. It can change, for instance, a symmetric ordinary difference equation into a differential equation. or symmetric, well, I guess, sorry, simply would be symmetric ordinary difference equation into a non-symmetric equation, or non-symmetric ordinary equation into a differential equation. So you have a bunch of transformations like this. And one of them at the very bottom is basically a differential equation with a nasty singularity, with a moderately nasty singularity to infinity gets turned into a differential equation with a moderately nasty singularity to infinity, which turns out to basically be the Fourier transform, an algebraic version of the Fourier transform. And so all of these things basically correspond, and a lot of things correspond to well-known integral transforms, like for instance, the Bellin transform is the thing that is the analog of going from ordinary ordinary difference equation to differential equation. The other version of this is taking the power series solution of an equation. You can also think of it this way: if the fact that you have a recurrence satisfied by the coefficients of if you do the power series method to solve an equation, you get this recurrence for the coefficients. That recurrence is the ordinary difference equation that you got transformed to. Now, there's two things that happen here, two consequences here. Firstly, all of these transformations preserve all of the isomoduli deformations. So if you start with something which has deformations given by Painlevé 6 and transform it, it'll still have deformations by Painlevé 6. And this actually gave new isomoduli interpretations of Painlevé 6 equation by using this transformation. Secondly, if it's rigid, there's going to be one of these interpretations, one way of turning it into a ruled surface, where the equation is completely trivial. You may need to blow up some extra points first, but there's always a way of basically turning it into a trivial equation if it's rigid. And as I said, these transformations are basically integral operators. And what this means is, at least formally, any rigid equation has a solution given by integrals. Now, this is only rigorous actually at the elliptic level, but it really does explain various integral representations, known integral representations of hypergeometric functions. Okay, now I mentioned derived categories. Now, one of the things that's nice about this, so this is getting into sort of really highfalutin stuff, but you have to do that the last few pages of colloquium, or else people will think everything you did was easy. So these non-commutative surfaces, they're derived categories, it turns out, are even simpler to describe than the original categories of Sheaves. So all of these constructions in the literature are relatively complicated. It turns out there's actually a very simple description of the derived category of any of these non-commutative surfaces. Basically, you just take the derived category of a commutative surface, break it up into two pieces in a particular way, and then glue them back together in a very slightly twisted way, which is again just parameterized by a point on this Jacobian. So it's just basically a point on, either an elliptic curve or a Q or a point or an additive group. And moreover, so of course, if I just give you the derived category, that doesn't tell you anything. That doesn't really tell you about the surface. But there's an extra structure you get called a T structure, which does cut out an abelian category from a derived category, and from a triangulated category, really. And it turns out there's also a simple description of the T structures. I mean, it's not quite as simple, but it's basically a relatively straightforward inductive description, just basically saying, okay, well, we got this by an iterated blow up. Well, then, each one of these blow down, every time we blow down or when we map to the curve we ruled over, each one of those maps should be a morphism. So we know what it's supposed to, it's supposed to be left exact. Well, it's supposed to be exact on the right side. And that sort of thing basically already gives you a lot of information about what the T structure has to look like. And so you get this nice, relatively simple inductive description of the T structure. Now, so some of these things like the fact that below us commute, the derived equivalence corresponding to that is actually easy to write down as well. And so all you have to do to show that you get that blowing up commutes on the level of abelian categories, you need to show that derived equivalence preserves the T structure. And that's how all of these arguments work. But there's some additional cases. If you start with an elliptic surface and deform it to a non-commutative surface, okay, then at least for a couple of cases like that, the deformation you get satisfies extra derived equivalences. There are two main types of commutative surfaces that arise here. They need to have a Poisson structure to have this nice deformation. So there's only two of them, two families. One of them is rational surfaces with a particular numerical condition, and the other are basically E cross P1 and deformations thereof. Each case, you get a two-parameter family of deformations. So you get one deformation where things remain commutative, and then one deformation where things become non-commutative. And there's an action of SL2Z on those two parameters, such that the derived category is invariant under that action. So I don't want to, it doesn't actually act on the family of derived categories quite. So there's some isomorphisms, autoequivalences that can possibly show up. But basically, if you act by SL2Z on the parameters, there exists a derived equivalence between the two fibers. One of those two classes of surfaces, if you look at the commutative deformations, those are exactly the surfaces arising in Sakai's construction of the Painlevé hierarchy. And this derived equivalence acts on that. So you get this SL2Z acting on that commutative family, and it turns it into a non-commutative family. And so you basically get a Q union infinity, you get a Q worth of non-commutative families, each one of which gives rise to an interpretation of Painlevé as a monodromy preserving deformation. And these are like higher order equations and typically they're never living on a trivial vector bundle. But also, if you look at the interpretation corresponding to infinity, i.e. the commutative family, that turns out to be exactly Sakai's original construction. You're basically classifying zero-dimensional sheaves of degree 1 on your surface, on this commutative surface. And in other words, you're looking at points on this commutative surface, and these birational maps that Sakai are doing are just maps between those moduli spaces. Okay. But the other thing is that we get these derived equivalences between non-commutative deformations and moduli spaces of differential equations. And those sorts of derived equivalences are exactly the kind of thing that people study in geometric Langlands theory. I mean, it's actually a slightly more complicated version of the typical geometric Langlands setup because we actually have singularities of our equation. So it's actually a little bit more complicated. And it's a second order equation. So this is really a non-trivial version of geometric Langlands that we're looking at. And we're generalizing it. This theorem generalizes it to allow to difference equations or elliptic difference equations or anywhere in that hierarchy. And so we get this. So this says in the two-dimensional case at least, where it's a two-dimensional moduli space, we have this generalization of geometric Langlands, where everything becomes discrete. And so this leads to a big honkin' open question, which I have no idea how to really approach, which is, is there something like this for higher dimensional moduli spaces? If you have more singularities or higher order equations, is there a discrete version of geometric Langlands? So the one thing we have there is we have the infinitesimal information that the moduli spaces have Poisson structures. And moreover, there's an infinitesimal, the deformations of a derived category are basically the same as the deformations of the commutative category. So the fact that there's this Poisson structure tells us that the derived category also has the same deformations, but because because equivalent derived categories have the same deformations, the autoequivalences of our derived category that we're starting with should act on these infinitesimal deformations. And the commutative relaxation always has this derived equivalence, always has a derived autoequivalence as we want. So this at least vaguely says that there's an infinitesimal version of geometric Langlands in the discrete case. So there's a pretty good reason to believe it ought to exist, but it's a big open question. And but that's sort of really the big next case, which will require probably higher dimensional non-commutative geometry constructions. So there's a lot of different ways that one try to approach this, but that's sort of the big indication that there's more to the story. But anyway, so I'll stop here, and hopefully I'll be able to see some of you all in November, and but anyway, so thanks for coming. Any questions? I imagine you can probably unmute yourself, or yeah.
I have a question. So when you say about non-commutative deformations of surfaces, it actually means deformation quantization, or you don't have
Well,
it?
so so you're right. So traditionally, there's an infinitesimal deformation theory, where you basically, so if you have a Poisson structure, you get this infinitesimal deformation, and it actually extends sort of analytically. You get this family of surfaces, you get this family over an analytic neighborhood if you've set things up right. But what I'm really looking at are algebraic. So basically what I'm saying is that if you take this analytic deformation just coming from the Poisson structure, you can actually integrate it all the way out. And it'll basically fill out a natural, something with a natural algebraic structure, which in the elliptic case is actually going to be compact and will be an elliptic curve.
Yeah.
And in the other cases, it's going to be a multiplicative group or an additive group.
So sorry, I missed the point. So
okay.
So
yeah, I may not have understood what you were asking.
So your answer is your non-commutative surface is actually not a deformation quantization?
Well, so basically, well, there's two types of non-commutative surfaces that arise in the construction. So some of them are just categories of sheaves that fit into a family, and none of the fibers are the categories of sheaves on a commutative surface. The interesting ones, if you look at the family of all of them, there's a codimension 1 subfamily where the category of sheaves becomes the category of sheaves on a commutative projective surface. So it is a quantization in that sense, at least. But you're deforming the category rather than really deforming the surface itself. Because if you try to deform the surface itself, it only really sort of works either infinitesimally or at least analytically. But the other thing is that everything is algebraic. So in bigger, one of the things I didn't mention is that everything works in finite characteristic, and actually some of the arguments require some of the things I can prove. The only way I know how to prove them is by actually reducing to the finite characteristic case. So there's definitely, it really is an algebraic theory in the end.
So in finite characteristic case, it corresponds to such, I don't know, arithmetic D module or something like that.
Well, yeah, I mean, basically, I'm not sure. Well, what it means for differential equations is, I mean, it's just basically, it's a finite dimensional algebra over a commutative surface. It's not too bad. It's none of the really complicated stuff that people look at with differential equations of characteristic P. It's the sort of stupidest thing you could think of for differential equations of characteristic P is the right thing. Basically, you just take that same algebra and say, well, it has a big center.
I see.
But actually, that ends up being key to some of the arguments. The fact that you have this commutative case down there, that's really just sort of this. That's almost commutative. There are things that are easier to prove when it's almost commutative, and then you just basically need to argue that those cases are dense. But it turns out you need some finite characteristic cases to make them all dense. But basically, yeah. But really, again, it's just the category of sheaves in the end. So the interpretation as equations is less meaningful in finite characteristic cases, especially if you're in an over finite field. I guess Q difference equations still can be meaningful in elliptic difference equations, but ordinary difference equations and differential equations, well, basically you have the same sorts of problems as you would have with Q difference equations when Q is a root of unity. So even in characteristic 0, if Q is a root of unity, Q difference equations are badly behaved.
I see.
The same kinds of, but the fact that you still have those, but those same sorts of things happen in finite characteristics for the differential and additive cases. But it turns out that those are actually useful cases to have around because they behave like commutative. I mean, they're, strictly speaking, Asimai algebras on commutative surfaces. I guess generically Asimai algebras. Anyway.
Yeah, thank you very much.
Yeah.
Thank you for the interesting talk.
Welcome. Any other questions?
Excuse me. Okay. Could you explain more specifically about geometric Langlands correspondence? I mean, maybe you know Dima-Lincoln showed geometric Langlands correspondence for P1 plus 4 points by using initial conditions of Painlevé 6. So my question is that what will you change his condition? What will you change his
well, so in the differential case, this is exactly the moduli space I'm looking at. Yeah, I guess Dima had mentioned at one point that, oh yeah, this is what this is. It wasn't clear to me whether he'd actually done it or whether, whether he had plans to do it or whatever. But yeah, but this is exactly it. But then the point, but the argument, my argument is completely different as far as I can tell. I basically write down, here's the derived category. And write down an explicit, well, basically in that case, it's basically, you can just write down, well, you can actually write down an algebra, an algebra that it's derived Merid equivalent to. And then you just basically show that the derived equivalences you want, you basically just modify. You just basically take that. You have this exceptional sequence. You just modify the exceptional sequence, this exceptional collection, and show that the exceptional collection, the algebra you get from the new exceptional collection, is an algebra of the same kind, and so it gives you a derived equivalence to a different surface. Now it's a bit more complicated in the different. I mean, a lot of these things are actually easiest in the elliptic case, because algebraic geometry is always easier when things are smooth. So there's extra complications when it's. I mean, in the differential case, it's not a strong exceptional collection, so there's like a DG algebra in the picture, but it's the same basic principle. You just modify the exceptional collection, and well, so and in fact, more precisely, well, right, it was, and this is also sort of where you can get this two-parameter family of deformations sort of directly in terms of the derived category. You basically start with a Del-Pezzo surface, take the subcategory of the derived category where there are no derived global sections. So I guess one of the orthogonals of the structure sheaf. And then you glue that back to the structure sheaf, and you also glue in an extra thing corresponding to blowing up a point. And so you get this semi-orthogonal decomposition with 3 pieces, 2 of which are just basically vector spaces, the derived category of vector spaces. But you have 2 parameters for how you glue those things back together, basically coming from in one case a line bundle on the curve, and in the other case a point on the curve. But it's the same basic data. And then you just modify that semi-orthogonal collection in a couple of different ways, and those gives you the 2 generators of SL2Z. They end up having the same form. So that's how, and sort of in the end, basically part of this construction uses the fact that, well, I mean, basically you get, in order to show that the algebra you get is the same, you basically changed your sheaves on your elliptic curve or degenerate elliptic curve, and then you need to do a derived equivalence, auto equivalence of the elliptic curve to put it back to what you want, to the form you want. But the basic idea is pretty straightforward. So as I said, it's easier in the elliptic case, and then you have to do some extra work to actually show that makes sense in the degenerate cases. But you do get all of the degenerate cases. But I don't know how to compare it to, I haven't actually seen Dima's argument. So I don't know how it compares. But certainly well, I should say, of course, that I'm slightly palming a card here because I'm getting a derived equivalence for these different moduli spaces of differential equations. I'm not sure I'm actually showing that the one that's supposed to correspond to D modules on the moduli space of vector bundles is actually the thing corresponding to D modules on the moduli space of vector bundles. I just have a direct construction of it as here's this non-commutative category. But but on the other hand, we understand the deformation theory of this derived I mean, we understand the deformation theories enough to basically say that it does basically have to be that whatever Dima is getting, because there's just nothing else it could be. But yeah, I mean, there's a little bit there that I'm not really showing properly, but it's sort of the general principle of there's a non-commutative deformation of the commutative relaxations, the modulations of Higgs bundles, and that non-commutative deformation is derived equivalent to the commutative moduli space of differential equations. I also should say I have no idea where the rest of my SL to Z lives in terms of Langlands. I mean, Langlands is basically just talking about one generator of this SL to Z, and I have no idea sort of where the rest lives in this picture. And thank you all, and have a good Saturday or Friday night, or maybe it's Monday somewhere. Who knows? Have a good day.